Thank you for taking the time to watch this video showing how you can design a typical project using our exciting new feature in StruCalc 10.0, which is Load Tracker. In this example, you will see the many ways that StruCalc can quickly calculate structural members in a project. I'll offer tricks that I've learned over my use of Load Tracker on many different projects to help you save even more design time. This project consists of a two-story building with an unbalanced roof design consisting of rafters supported by two ridge beams. There is a column supporting these two ridge beams, which is supported by a floor structure below. We will start by designing the roof rafters. We will begin by designing the rafter with the longest span, which is labeled RFT1. The interior span of this rafter is 16 feet and has a 2-foot overhang. We'll use the rafter module. Plug in that information and use auto size and determine we should use a number 2 Doug fir 2x12 rafter spaced 24 inches on center. We'll save that result. Now we can quickly size the rest of the rafters for this roof assembly. We'll now design rafter RFT2, which is a 10-foot interior span and a 4-foot overhang. Using the last rafter design, we will rename it RFT1 to RFT2 and put in the design information, modify the rafter span, the overhang, and change the roof pitch to 512. We could probably change the size of these rafters, but to keep this roof design simple, we will use 2x12 rafters spaced 24 inches on center and save that result. This roof also consists of an 8-foot dormer. We will design rafters RFT3. They have a 12-foot interior span and a 1-foot overhang. We will rename it RFT3, put in the design information, including a 312 roof pitch, hit calculate, and find it is adequate, and save the result. We also have short rafters hanging off the dormer wall, which we will call RFT4. These rafters have a 4-foot interior span and a 2-foot overhang. We will again rename it, put in the span information, including an 812 pitch, and save that result. Now we can start designing the roof beams for this project. We'll first design roof beam RFB1, which has a 20-foot span and supports rafters RFT1 and RFT2. We'll design this by using the multi-span multi-loaded module. We put in the 20-foot span and use the uniform load hyperlink to input these roof loads. Simply click the hyperlink, pick RFT1 from the list, select reaction A, and these reactions will be dropped into the analysis. We can also add rafter RFT2, select reaction A, and this completes the loading on this beam. You can see on the loading link box where we have added rafters RFT1 and RFT2, and you can see that the reaction from these rafters have been converted into a uniform load on the span. We can now change the default of this analysis to a roof beam. By clicking the roof beam default, you can see that the roof beam deflection limits and duration factor are applied to this design. Now we will auto size and select a 24F V4 glulam beam and determine that we need a 5.5 by 13.5 inch glulam for this design. We will save that result. Next, we will design RFB2. This is a 24-foot long beam and has the back wall rafters RFT2, portions of roof using RFT1, and the dormer rafters RFT3. We will auto size the previous RFB1 beam design and rename it RFB2, as well as change the span to 24 feet. For the uniform load, we still have the loading from Rafter RFT2, but as you can see, we do not have RFT1 across the entire span. So we'll delete RFT1 from the loading link box and put the different rafters in the hyperlinks located in the trapezoidal input boxes. You can see that Rafter RFT1 extends from the end of the beam to a distance of 6 feet across the span. We will click the hyperlink for trapezoidal load 1, select RFT1, pick reaction A, and put the loading from 0 to 6 feet on the beam span. Next we will add dormer rafters RFT3. Using the trapezoidal load 2 hyperlink, we select RFT3, pick reaction A, and input its load location from 6 feet to 14 feet along the beam span. You can see that as we add these loads, they will appear on the loading screen and also in the loading link boxes. Now we can complete the load design by adding the remaining rafters RFT1, using the trapezoidal load 3 hyperlink, pick RFT1 and reaction A, and set the load location from 14 feet to 24 feet on the beam span. We can now check to see if the same beam works by clicking the Calculate button, and we will find that it does not. Using auto size, we determine the final size requirement to be a 5.5 by 15 inch glulam beam. We will save that design. Now we can design column COL1, which supports the ends of RFB1 and RFB2. We'll open the column module. It is a 12-foot long column that is unbraced to full length in both directions. We now pick the column hyperlink to put it in the reactions of the beams. We will choose the left reaction of RFB1, add it to the design, continue by adding RFB2, and based on the loading diagram, we will choose the right reaction of this member. These two beam loads are summed together as shown on the screen. We will try a solid saw number 2 dug for a column, auto size it, and find that a 6x6 post will work for these design conditions. We will save that result. Now we will design the floor framing for the structure. We will design the floor joists first by analyzing the joists JST1, which run left to right and are supported by beam FLB2. You can see from the framing plan that this is a multi-span joist with spans of 12 feet and 14 feet. We will select the floor joist module and put in the 12-foot and 14-foot spans. And using auto size, and although a 9.5 inch TJI 110 spaced 16 inches on center will work for the design, we will select the 11 7/8 inch TJI 110s. We will save that analysis. Joist JST2 has spans of 18 feet and 8 feet. We will make a copy of the previous joist design by renaming it and calling it JST2, and modify the spans to lengths of 18 feet and 8 feet. By hitting the Calculate button, we have determined the same joists are adequate, and save that analysis. Now we want to design joist JST3. You can see from the cross-section that these joists support the dormer wall. We will first design the dormer wall by using the wall design module. We will name this Wall 1, put in the wall height of 8 feet, and leave the wall default dead load as 10 pounds per square foot. We can now click the hyperlink and add the B reaction from RFT2 and the A reaction from the short rafters RFT4. We will try the default design of 2x6 studs spaced 16 inches on center, hit Calculate, and find that it is adequate, and save that design. We can now take the previous design of Joist JST2, make a copy by renaming it JST3, and now we can add the wall 1 load to the joist span. We click the hyperlink for the center span, select wall 1, add it to the design, and set the wall load distance at 4 feet from the left reaction. You can see that this load appears on the loading diagram as well as the loading link box. When you hit the Calculate button, you will see that these joists have now become inadequate. We will try a heavier joist, like an 11/7/8" TJI 360, and find that it is now adequate, and save that design. We are now ready to design the floor beams. You can see from the diagram that we have roof column COL1 bearing on beam FLB1, located between the beams FLB2 and FLB3. Since this beam FLB1 may be used in place of a floor joist, we will use a simple span floor beam module for this analysis. The span on this beam is 12 feet, and we will use a tributary width of one joist space, which is 16 inches or 1.33 feet. Because the majority of the load on this beam will be coming from column COL1, which supports the roof beams, we will use a duration factor of 1.15, representing roof snow loads. We can add the column COL1 load by clicking the hyperlink and inserting the load from column COL1. This column is located 8 feet from the left end. By clicking Auto Size and using a 2.0 microlam, we have determined that we need 4 1 3/4 by 11 7/8 inch LVLs to support the loads. I'll save that analysis. Now we can design floor beam FLB2, which is a multi-span beam with spans of 14 feet and 12 feet. We'll open up the multi-loaded multi-span module, put in those spans, and use the uniform load hyperlinks in the center reaction of joist JST1 on both spans. One of the many benefits you get from Load Tracker is a more accurate calculation of the required loads on a span. Most designers would design the loads on this beam based on 1/2 the tributary length of the joists on each side of this beam. You will find that this is an unconservative assumption. Using this design method, you would get a total uniform load on this beam of 715 PLF. When you use the more accurate design from Load Tracker, you'll get a uniform load of 898 PLF, which is 25% higher. We will now complete the design of this beam by adding the point load from floor beam FLB1 on the left span. Click the point load hyperlink, grab the beam reaction from FLB1, and input the location at 10 feet from the left end support point. By auto-sizing, we have determined that a 5.5 by 16.5 inch glulam beam will be sufficient to meet the design criteria. We can now save that analysis. We can now design floor beam FLB3, which has a span of 18 feet and supports the left reaction from joist JST1. We'll open up the multi-loaded multi-span beam module, put in the 18-foot span, select the uniform load hyperlink, select JST1, and pick the A reaction to place that load on the beam span. We also have the point load from beam FLB1. Click the point 1 load hyperlink, pick FLB1, and select reaction A, and put its location 2 feet from the left end. Using auto size, we find that a 5.5 by 12 inch glulam beam will work for this design, and save that result. I will now size the header located on the left side of this plan. It has a span of 12 feet and supports rafter loads and joist loads. For the first 8 feet, it supports the short rafters RFT4 loads and the joist JST3 joist that support the dormer wall. I will open up the multi-loaded multi-span B module, name it FLB4, put in a 12-foot span, use the trapezoidal load 1 hyperlink, pick joist JST3, select the reaction A, and also add RFT4, and select reaction B. We will set the location of these loads from 0 feet to 8 feet. We also need to add the reactions from joist JST2 and rafter RFT1. Using the second trapezoidal load hyperlink, we will put in the loads JST2, reaction A, and also RFT1, reaction B. These loads will be summed up, and we'll place them at a distance from 8 feet to 12 feet. Since a large portion of these loads are from roof rafters, we will use the roof beam defaults for this header. We will try a solid sawn header, auto size, and find there are no feasible options. We will switch to a structural composite, try a 2.0 microlam, and find that 3 laminations of 1 3/4 by 9.5 inch LVLs will work, and save that design. As you can see, LoadTracker saves a tremendous amount of time, as we are able to design 15 members for this project in a very short amount of time. Well, you'll find that LoadTracker can save even more time if you have to make design changes for this project. Let's say, for example, we made a mistake and found that we were supposed to design the roof for 35 pounds per square foot roof loading instead of the 25 that we used. I will now show you how we can quickly update this design. We will open up RFT1, change the loading, hit calculate, and find it is now inadequate, and change the spacing to 16 inches on center. Hit calculate again. It is adequate now, and resave it. We'll also do that with rafter RFT2. Hit calculate, find it is still adequate, and resave it. We'll do the same thing with RFT3 and RFT4. Now we can check to see if any of the other project members have become inadequate due to these changes. We can go to the LoadTracker tab, hit Calculate Project, select Calculate All, and now LoadTracker will cycle revised calculations through the entire project and let you know which members have become inadequate. You will now be given the option to open all the members that have become inadequate. In this project, there are now 3 members that have become inadequate. I will open up column COL1, select auto size, and find that I now need an 8x8 post, and resave it. I will open up RFB2, select auto size, and find that it now needs a 5.5 by 16.5 inch glulam beam, and save it. Finally, I can now open up FLB2, auto size it, and find that we now need an 18 inch glulam beam, and resave it. As you can see, in just a few minutes I was able to make the appropriate changes to update all the design members in this project. As you can imagine, having to update these calculations manually, even using StruCalc, would have taken a considerable amount of time. We will now design the lower floor column, starting with column COL2, which is the middle support for floor beam FLB2. Open up the column module, Put in a height of 8 feet, click the hyperlink, and put in reaction B of FLB2. Using auto size for number 2 dug fir post, we find that an 8x8 post is needed to support these loads, and we will save that design. We will now size column COL3 at the back of the building, which is 6 feet tall. Open up the column module and name it COL3 with a height of 6 feet. We can then use the hyperlink and pick FLB2, reaction A. We'll assume that a number 6 dug fir 6x6 post will work. Hit calculate and find that it does, and save that result. We will now design column COL4, which supports beam FLB3. We will rename column COL3 and call it COL4. Put in a revised height of 8 feet. Clear the FLB2 load on the load link screen and add reaction A from beam FLB3. By clicking the calculate button, we find that the 6x6 post works and save the design. We will now design column COL5, which supports beams FLB3 and FLB4. It is also an 8-foot column. We will click the hyperlink and select reaction B of FLB3 and reaction B of FLB4. We will try 4 laminated 2x6s and find that it works to support these loads and save that design. We'll finish the column design by sizing column COL6, which supports beam FLB2. It is also an 8-foot column. We will click the hyperlink, select reaction C of FLB2. We will try 4 laminated 2x6s and find that it works to support these loads and save that design. We can now quickly design the footings for this project. We will start with footing FTG1, which supports column COL2. We'll go to the footing module, click the hyperlink, and select column COL2. Hit the calculate button and find that we need a footing width of this much, so we will use a 4-foot 6-inch footing. Hit calculate and save it. Footing FTG2 supports column COL3. We will name the footing FTG2. Click the hyperlink to add that load. Press the calculate button, and we find that this footing is required. We'll put in a footing width of 2 foot 6 inches for this design. Hit calculate and save it. We will now design footing FTG3, which supports column COL4. Since it has a similar load as FTG2, we'll make a copy of that design and rename it FTG3. Delete column COL3 in the load link screen and add column COL4. Hit the calculate button and find that a 2 foot 6 inch footing is still adequate and save it. We can do the same for footing 4, which supports column COL5. Rename it FTG4. Delete column 4 and add column 5. Hit calculate and find that this footing width is required. We will try a size of 3 feet. Hit calculate and find that it is adequate and save it. The last square footing we will design is footing FTG5. We will rename the footing FTG5, delete column COL5, and add column COL6. Hit Calculate, and find that a 2-foot square footing will support this column load. We'll make that change and save it. The final element of design I will show in this project is the continuous footing along the back wall of this project. We will first design the support wall for this area. We will open up the wall module, call it WALL2, and select a 2-story loading. The upper wall is 8 foot tall, which we will input in here, and the lower wall is 6 feet in height, which we will put in here. We can now use the load tracker to add the loads from Rafter RFT2 and Joist JST3. Click the hyperlink and add the B reaction of RFT2 and the C reaction of JST3. The loads from these members are summed up at this location. You can also add a lateral design pressure on this wall. We will assume a wind design pressure of 20 psf loaded on this wall. Hit Calculate, and as you can see, the default design of 2x6 studs spaced 16 inches on center will work for this design, and save it. We can now design the continuous footing for this wall. We will open the footing module, select the continuous footing option, call this footing FTG6, and add the wall 2 load using the hyperlink. We will put in the stem wall height of 24 inches and leave the 8-inch stem wall width as is. Hit Calculate and find that the required footing width is less than a foot. For this design, we will select a 16-inch width and save it. We are now done with our project. You can print all your members using the Print Project option. You can also get a report which shows all the members that are linked using Load Tracker. Hit the Load Tracker tab and select Summary Report, and you can get a printout of all the Load Tracker links between your project members. We hope this video helps show you the powerful capability of Load Tracker and demonstrate a few ways of how you can use it even better. If you have any questions regarding StruCalc or Load Tracker, please call us at 1-800-279-1353. Thank you for your time.